So it's the conference talk, and yes, it's Madeline.
Yeah, I'm just waiting if because we have offline attendees, if they are ready. Let's wait for Hari Krishnan to confirm.
Okay. We can start it.
Oh, okay.
No, I think we can start already. Yes, he will be joining us later.
Okay, perfect. Okay, because we're joining from different zones, so good morning and good evening from wherever you're joining us, and good afternoon from here. It's my pleasure to chair this session and to introduce our speaker, Dr. Saba. She's the Vice Dean of Students Affairs and Associate Professor in the Department of Mathematics at Tafila Technical University, Jordan. She has earned her PhD in 2015 from North Dakota State University, United States. And her research interest spans several areas in algebra and in graph theory, including commutative algebra, combinatorics, algebraic graph theory, and fuzzy algebraic structures as well. She has published extensively in reputable international journals and conference proceedings, and has made a valuable contribution to these fields. I have had the pleasure of collaborating with Saba on several research projects, and I have also the pleasure of meeting her in person 2 times in Abu Dhabi. Beyond mathematics, something secret about her, she loves a lot traveling, and because of that, now you're seeing her in Germany. And this reflects her curiosity and openness to exploring new places, cultures, and perspectives, qualities that they are equally valuable as well in research. She will present today about graphs associated with prime-absorbing hyperideals in hyperrings. So please join me in giving a warm welcome to Saba. Saba, the floor is yours.
Thank you, Madeline, and thank you for a nice introduction. Really, it's my pleasure to work with you and hopefully to continue working. And also my pleasure also to say also again hi to Professor Ahmed Erfian. So also he's one with us today who is working with him a lot in many papers or research. And today, my talk will be on a graph associated with the prime absorbing hyperideal in hyperring. So for my talk today, I will start just like to tell you about my motivations, why hyperring, and how I do a joining between a graph theory at the beginning with abstract algebra like ring and groups, and then between a graph theory and this new research before maybe 4 months, start working with Madeline, Professor Ahmed, with something related between graph theory, algebra, and also the hyperrings in general, similar to what we did already before. So in new research work, I associate with prime absorbing hyperideal, and I gain many results related to the basics properties like connectivity, diameter, clique number, and chromatic number, and non-obvious examples we did. And it's why we studied. I will start why we study graph erasing from hyperring. So before 5 or 6 years ago, all our joint work between graph theory and algebraic, for example, we're working with rings, we're working with a group, something related to, connections between a graph theory, algebra. But this time we're working with a graph theoretical method, provide a powerful framework, and this is investigating algebraic structure from different points. So they often revise structures properties that are difficult. Really, this time is totally difficult than before because in the last few years, we just using purely algebraic tool. Now we change to the another powerful frameworks with hyperrings. So all the other authors working with the normal, purely algebraic tools. So Professor David Anderson worked with zero divisor graphs and also annihilating ideal graph, intersections graphs, and total graphs, and so on. From this, we're trying to use similar ideas from purely algebraic tools and to extend our work with hyperrings. This is what we did on this year. So our goal again, construct a graph, associate this time with the prime absorbing hyperideal. By the way, absorbing high ideal, just when I look to another research, it just started as an absorbing hyperideal in 2022. So I got this definition newly on 2022, and then we used the word prime, and now in 2026, I'm trying to use a graph theory and do intersection between graph theory and the prime absorbing hyperideals. And then we're trying to investigate how the algebraic properties of hyperring are reflected in graph properties. For example, again, like what we did all the time, trying to figure out some theorems and results related to connectivity, complete, the girth, and also how is the graph look like under finite ring. And all the time we work with some basic examples, for example, Z12, Z6, Z, for example, Zn, and find some results about it. Like other presenters before, in the last 2 days, everyone go over the definitions of hyperrings, and I think all of us now familiar with. And just a good remark to notice that ordinary rings are a special case of hyperrings where every hypermultiplication produce exactly one elements. Okay, again, this is the definition of hyperideal. Okay, and I think the other representatives go over. Okay. So why are prime? Okay, we just focus on not just in our hyperideals. In this research work, we also focus on a prime hyperideal. So why are prime hyperideals important? So because it's play a crucial role in the structural theory of hyperrings, and of course they generalize the prime ideal in our classical ring theory. So before 5 years, we working just for me in classical ring theory. And then now the generalization of a prime ideal in classical ring. So now with our hyperrings, so we can get more generalized and extends more results. So let's all together remember what is the meaning of two absorbing ideal in classical definitions. So if R is a commutative ring and I be a proper ideal of R, then I is called a two absorbing ideal. I'm talking now about the classical definitions. So if we have, again, when we call I is it's called a two absorbing ideal, if we have two elements in R, A, B, C. So if A, B, C belong to this I for A, B, C in R, then at least one of the following holds. Maybe, not maybe, so A, B in I, or A, C in I, or B, C in I. So in this case, we can tell that I is called a two absorbing ideal. So again, the notation of two absorbing ideal was introduced by Dr. Ayman al-Badawi, and this was in 2007. So he defined this as a natural generalization of a prime ideal. So this kind of generalization of a prime ideal, the two absorbing ideal. And it's good to know that also every prime ideal is two absorbing, but of course the converse is not true. And in his paper, he wrote some examples about the contradictions by a good example. So just to make everything clear, before we starting with our definition, Okay. For example, Z, what they call it, Z6, the ideal for
Saba, it's freezing from your end. Colleagues, are you able to hear or see now?
No, now no.
Oh, okay, so I thought that the problem is mine, although I'm working from campus.
No, it's not yours.
So let me just message her. I think that she lost connection because I'm sending her WhatsApp and it's not delivered by her. I tried to call her also because she's out of the country, so her phone is out of service. So what do you recommend, Hari Krishnan? Would you like that we go with Professor Ahmad Irfanian, and when he finishes, because it's closely related, the topics, when she joins, she can continue? Hari Krishnan, are you hearing me?
No, he is not there in the room right now.
Okay, so the organizers that they are in the room, Dr. Saba, I think she lost internet connection.
Yes.
I'm trying to reach out to her with no answer because no internet at all. So would you like to continue with Professor Ahmad, and if she was able to join in 30 minutes from now, she can continue after?
Yeah, I think we will wait for 2 minutes, and then if she doesn't join in 2 minutes, then we'll continue with Professor Irfanian's talk. Is that okay?
Yeah,
Okay.
yeah.
Right. Okay. Thank you.
So, Professor Irfanian, good afternoon.
Let's look at that. No, muted. First, we will tell that we will continue. Yes, I'll be. Hello, Medline. We will go with the next session now. So
Yeah,
if Saba can join for the next session after Irfanian's talk, then we will continue.
We'll inform her. We'll inform
Okay.
her.
Okay. Thank you.
Hello. Hello, Professor Ahmad Irfanian.
Yes, how are you? Can you hear me?
Yeah.
Okay.
Good afternoon. India.
So
Are you able to hear me?
let me share.
Yeah.
Here it is. Here it is on your.
Okay.
can talk.
Can you see?
Yeah, yeah.
Can you see the slide, Madeline?
Yes, yes.
Yeah, we're seeing your
to-
slide and seeing you perfectly.
Yes,
All
2
right.
minutes. Professor Shyam Prasad will introduce you 2 minutes. Then after that you can start.
Okay.
They are able to hear, right?
Am I audible, Professor Irfanian?
Yes, I'm ready.
Okay. Okay, good afternoon.
Okay, thank you very much. So
Yes.
I'm sorry that I could not able to attend in face. So
Yes.
hopefully in the next year we will have a conference on group theory, and I
Yes.
hope to be available in
Definitely.
the
Yes.
university. Yes.
Yes. We'll make sure that you should come here. Yes. All of you.
I hope
for-
so.
Hope so. Yes. All of you. Yeah.
Thank you.
So I just give brief introduction about you, and then you can start your presentation.
Okay, so
Yes.
I can start or wait for another 2 minutes.
Yes. Yes.
I can start
No, no, no. You have to wait for another 2 minutes. Yes.
another 2 minutes. Okay.
Yeah. I will
All right.
introduce now. Afterwards, you can start.
Okay.
Okay. Professor Ahmed Irfanian is a professor of mathematics at Ferdowsi University of Mashhad, Iran, a distinguished mathematician. He earned his PhD in group theory from Cardiff University, UK, and has been serving as full professor since 2010. Professor Irfanian's research interests include combinatorial and probabilistic group theory, finite simple groups, graph theory, combinatorics, and algebraic structures. He has published around 200 research papers in leading international journals, authored several books, and has successfully supervised 45 masters and 20 doctoral students. He has also held key academic leadership positions, including Dean of the Faculty of Mathematical Sciences and Head of Department Mathematical Sciences Planning at Iran's Ministry of Science, Research and Technology. His outstanding contributions to research and education have been recognized through numerous prestigious awards, including the Distinguished Full Professor Award and the Distinguished Professor of Teaching Award. So with this brief introduction, I invite Professor Irfanian to give this talk entitled The Hyperoperation Incidence Bipartite Graph of a Finite Poly Group. So welcome you, Professor Irfanian. Nice to see you. You can
Okay,
start the presentation.
All right. So thank
Yes.
you very much for Prasad.
Yes.
So first of all, I would like to thank the organizer for Prasad for organizing this nice conference on hyperstructure. So we do not have many conferences on this area. So most of conferences are in maybe general algebra or group theory or ring theory. So in specific topics, we do not have many conferences. So this is a good opportunity for us to mention something in hyperstructure, in polygroup, and so on. So before I start, let me give announcement for the group theory conference. So as for Prasad now, so we will have a biennial international group theory conference every 2 years. And so it started from 2011. So it was in Malaysia, it was in Indonesia, in South Africa, in Iran, and also one time in India. And next year we will have this conference in this university. So let me invite all of you to attend in the Biennial International Group Theory Conference next year. Now, what I would like to mention here to give some relations between algebraic structure and graph theory. So if you consider these two topics, algebraic structure means is the general area of algebra. So it includes groups, rings, and semigroups, and particularly hyperstructure, polygroup, and so on. So these topics belongs to algebra, which is a branch of pure mathematics. And on the other way, we will have graphs and discrete mathematics, which belongs to applied mathematics. So that's a combination between topics in pure mathematics and topics in applied mathematics. So I'm going to give a relation between these two topics, and as you know, the combination between algebraic structure and graph theory is algebraic graphs. So it's a very long history about algebraic graphs. So if you know, so the first algebraic graphs introduced by Cayley. So Cayley graph is a graph associated to a group. So it means that this is the first combination of algebra and graph. We will have many graphs associated to algebraic structure, but mostly are graphs associated to group. For example, commuting graph of a group, non-commuting graph of a group, power graph of a group. So that's all some of examples on graphs associated to groups. And also we have some known graphs associated to a ring. For example, zero divisor graph of a ring, intersection graph of a ring, Cayley graph of a semi-ring, and also annihilating graph related to R module, and also the graph which Dr. Saba mentioned just before me. It was one of algebraic graph, one of graphs associated to a ring and hyperrings, right? So recently I have some also papers on non-commuting graph associated to Lie algebra. So this is another topics in algebra which we can deal with that. So Lie algebra is one of topics in algebra. So it means that we can associate a graph associated to Lie algebra. Now, for hyperstructures and polygroups, we do not have many graphs. So as far as I know, so there are some papers by Prof. Madeline about the commutativity degree, and also commuting graph or non-commuting graph related to a polygroup for elements and for subgroups. So we do not have many papers on this area. So what I would like to mention here is to introduce a bipartite graph associated to a finite polygroup. Most of graphs defined on algebra structure are not bipartite. So if we consider bipartite graph, so also we do not have, even for a group, we do not have many graphs, many bipartite graphs associated to a group. So here is opportunity for me to introduce a bipartite graph associated to a finite polygroup. So we assume that finite polygroup because we are interested to have a finite graph. So we would like to have finite vertices and finite edges. So that's the reason that we always consider that the polygroup or group or ring are finite. Right. So as you know, let me just give a very short definition about bipartite graph. First of all, we know that we assume that the graph is simple. So what's the meaning of simple graph? Simple graph means that we do not have any loop or any multiple edges. So if we have these situations, then the graph is simple. But what's the bipartite graph? Bipartite graph means that the vertex set is the disjoint union of two subsets. Let me set left subset and right subsets, right? So we do not have any edge in any subsets. So it's equivalent to say that both sets, left sets and right sets, are independent. If we do not have any edges in a set, in a subset of a vertex set, then the set is independent. So we have two independent sets, but if we have an edge, so must be one ends in the left set and another ends in the right set, right? So this is a bipartite graph. Now, you know the definition of polygroup. I just remind a definition of polygroup very quickly. So when we are talking about a polygroup, is that we have a non-empty set. Usually we denote by P, capital P. We have identity elements. So we have inversion, and also we have a binary hyper operations. So this is the just material which we need for the polygroups. But we should have some axioms, some conditions that satisfying these conditions. So we have three main conditions. The first one is associativity. So we should have this relation. So for any three elements, X, Y, and Z, so we have X or Y, and then combined to Z is equal to the combination of X with the Y or Z, right? And also we should have identity property. So for any elements X, so E or X, so let me say the hyper operation by O. So E or X is equal to X or X is the singleton set X. And also we should have the reversibility. So we have to inverse. So if we have this situation that if X is an element in Y or Z, then Y belongs to X or Z inverse, and Z belongs to Y inverse or X. Sometimes we may have another condition, which is the commutativity, similar to a group. So if we have this condition that X or Y is Y or X, then the polygroup is a commutative polygroup. Let me give two examples of commutative polygroup and just non-commutative polygroup. So look at this example. If we have set P consists of the elements, identity E, A, and B with these conditions. So the inverse of E is A, inverse of A is B, inverse of B is A. And also we may define the hyper operation like this. So E or X is X or E is the singleton set. And also, you know, we will have A combination with A is the set of two elements E and A, and B or B is a set of two elements E and B, and A A and B and A, they are, that's the reason that this polygroup is commutative, is the identity. So you can just see that this set P with this identity operation and hyperoperation and inverse is a polygroup, so satisfying three conditions. So this is example of commutative polygroup of order 3. Now let me give another example of polygroup of order non-commutative polygroup of order 4. So if we consider P consists of 4 elements, so E, A, B, and C, and that's the relations. So just show you this is the relation, and you can see that here is non-commutative because AOC is not equal to COA. So AOC is the set of 2 elements A and C, but COA is the singleton set consisting A, right? So that's the reason that this is non-commutative. So this is example of non-commutative polygroup of order 4. Now let me just start the definition of the graph, just the new graph, new bipartite graph associated to this polygroup. So suppose that P is a finite polygroup with just hyperoperation. Again, we denote by O. And we are going to introduce a bipartite graph. So for bipartite graph, as I mentioned, we have to introduce the left and right sets, which are disjoint, and that they are independent set. So the left-hand side of the bipartite graph, I assume that the Cartesian product of P and P. So P cross P consists of all pairs X and Y such that X and Y are in P. And the right-hand side, I assume that just P. So you can see that we do not have any intersection between left and right sets. So that's disjoint. So this is important for defining that graph. Is very important to have no intersection between 2 sets. Now, how about the edge between the pair in the left-hand side? So if we consider a pair X and Y in the left-hand side and the element Z in the right-hand side, so we can say that X, the pair X comma Y, is adjacent to Z if and only if Z belongs to X or Y. So if Z belongs to X or Y, then we will have an edge between the pair X and Y and Z. This is the definition. So you can see that when we have, so if you see the edge set, so what's the edge set? Edge set consists of just all pair of 2 vertices, the first from the left-hand side and the second is from the right-hand side, and with the property that Z belongs to X or Y. So this is the definition of bipartite graph. When we define a graph, so some things are important. So the first one, we have to see that do we have isolated vertices? Is the graph connected? If the graph is connected, so what we can say about the diameter and what we can say about the gears, right? And then we may ask many things about the graph. So this is important. The motivation of defining a graph associated to a group or ring or in general in algebraic structure is to give some relations between algebra properties and graph properties. So this is very important. For example, I may ask this question. So we have a bipartite graph. You can probably know that we have complete bipartite graph. Complete bipartite graph means that every vertex in the left-hand side must be adjacent to all vertices on the right-hand side, and the converse. From every vertices in the right also is adjacent to the left-hand side. Now, the question is that, can we classify our polygroups or finite polygroups in such a way that the related bipartite graph is complete bipartite, right? So for what sort of polygroups we have this situation? So this is just a question in algebraic structure. So we are to classify or polygroups. So we have to see that when we have this situation for polygroups, right? So it is very important. So it's easy to see that the vertex on the left-hand side. So if you take a pair x and y, then the degree of x and y is at least 1. That's because x or y is a non-empty set. So if it has at least one element in the set, so that element is adjacent to the pair x and y. So it means that in the left-hand side, the degree of any vertex is at least 1. Now let me just consider the first example and see that what's the related graph, this graph, right? So if you see, we have 3 elements in polygroup P, right? So the left set is P, the Cartesian product of P and P. So we have 9 vertices on the left-hand side, right? So you can see that we have 9 pairs. And on the right, we have 3 elements. So the vertex set of this graph, which I just put the notation as the hyperstructure identity polygroup for that. So it consists of 2 sets. Set the left set and the right set, right? So we have 12 vertices, 9 in the left and 3 on the right. Now this is the graph. So you can see that. So this is a graph, means that identity in the bottom, if identity is adjacent to the pair E and E, because E belongs to the EOE, and A is adjacent to the pair E and A, because if you just see the definition of EOA, right, in the first example, EOA here, if you put X, if you put X is A, so EOA is equal to A. EOE consists of singleton elements A. So it means that A is adjacent to the pair E and A. So this is the bipartite graph here. So you can see that the degree of any vertex in the left-hand side, which is here on the top, right? So the degree is at least 1. So E and E has degree 1, but some of them has degree 2. For example, the pair A, E and A has degree 2. And in the second on the right, which is here on the bottom, right? Here, the degree of identity is 5. The degree of A and B are 3. Now, let me move to another example. This is example 2. That's a non-commutative polygroup of order 4. So you can see that the left set has 16 vertices, right? And the right, we have 4 vertices. Now here is a graph. So you can see that we have many edges, right? So on the left, we have 16 pairs, right? And on the right, we have 4 vertices. And you can see that the identity and C has degree 6, but A and B has degree 4. Now let me give some basic results about this graph. The first thing is that the number of vertices is the order of P squared plus P, because we have L, disjoint union of L and R, left-hand side and right-hand side. So we have order of P squared, just the order of P squared pairs in the left and P elements on the right. So this is the number of vertices. Now you can see that the number of edges is enough to consider the sum of all x or y. So we have to see that by our definition, x or y consists of how many vertices? So if we count all elements in the set x or y for any elements x and y in a polygroup P, then we will have the number of edges. Now, as I have already mentioned, so for any vertex in the left, the degree of elements in the left, which is a pair, is at least 1, and the degree of any vertex on the right depends on the number of pairs x and y, such that z belongs to the set x or y. Also, it's interesting to see that for some special kind of vertices, we can find the exactly degree, right? So the degree of the pair E and X, and also X and E, is 1, and we can see that we have unique neighbor. The unique neighbor for the pair E and X is X, and also for the pair X and E. Now, if we have an edge between the pair X and Y and Z, X and Y in the left and Z on the right, then we can see that the pair Z Y inverse is also adjacent to X. And moreover, X inverse, the pair X inverse Z, is also adjacent to Y, right? That comes from the definition and from the the property conditions for a polygroup which we have. Now, one of a special kind of polygroup is a group. So if P is a group, then you can see that the graph is a star graph. So we will have just number of G, or order of G elements in the left and right is only 1, which is identity. Another property is that when the graph is connected, so this graph is not always connected. So the connectivity comes from these conditions that if for every distinct elements, Z1 and Z2, so if we have two distinct elements, Z1 and Z2 in P, if we have a pair, a vertex on the left, so I just consider 2 vertices on the right. So if we have a vertex on the left such that the vertex on the left, which is a pair x and y, is adjacent to z1 and z2, then the graph is connected. Also, we may have so this is equivalent to this condition that if for every x and y, x or y contains at least two elements, right, two distinct elements, then the graph is connected. Now, it's interesting to consider the adjacency matrix for this graph. You know that the adjacency matrix is a matrix. The rows and columns are indexed by vertices, and we have 0 and 1. So if a vertex, for example, I is adjacent to j, so the entry ij is 0. If we don't have an edge between I and j, and if we have an edge is 1. So this is a symmetric matrix, and we may find the eigenvalues for the matrix. So I found that the maximum eigenvalues for this graph is the root square of n times the maximum degree of vertices on the right hand side. Now, just finally, let me give some open problems. We have many problems, and that's they are interesting if we can deal with this sort of open problems. These problems actually comes from the algebraic structure and also for the graph structure. Now, the first open problems is that can we characterize so it means that, let me explain here. If we have a bipartite graph, right? So can we find polygroup such that the related bipartite graph is the given bipartite graph, right? The second open problem is to find some relations between two polygroups such that their graphs are isomorphic. So we have isomorphism between two graphs. If we have two polygroups, P1 and P2, and their graphs are isomorphic. Isomorphism between two graphs means that we should have just bijection between two vertices, the vertex set of two vertex sets of P1 and P2, and they preserve H. So if we have an H in P1, so the image of that isomer, that map must be also an H, right? So what conditions we can put on P1 and P2 such that we have isomorphism between two graphs? The second open problems is that can we able to characterize or polygroups such that this bipartite graph is connected? Because you can see that I mentioned that this graph is not always connected. So for what kind of polygroups the graph is connected? The open problem number 4 is if the graph is not connected, so we will have connected components. So what we can say about the number of connected components, and also give this number in terms of some algebraic invariance. And the question, open question for problem number 5 is that classify all finite polygroups such that this graph is planar. Planar means that we can able to draw a graph in such a way that we don't have any intersection between two edges. And also, if you consider the adjacency matrix or Laplacian matrix, so can we able to find a formula for the energy of this graph? So that's some sort of open problems. And if any of you interested on this direction, just you can contact me. And this is some things between graphs and hyperstructure and polygroups. Thank you very much.
Wonderful presentation, Professor Irfanian. Any questions, please? Any questions online?
Thank you, Ahmad. Thanks for the nice presentation and for your way in making things very simple and very clear. And I'm glad that you're working on this part and relating it to polygroup. We already started some work. Me, you, and Saba, we worked at a little bit for group theory. We work on bipartite graph, and then we extended to polygroup, but it wasn't bipartite. And of course, definitely me and Saba will be included in more work related to graph theory and connecting it to polygroups. We have lots of ideas. We just need to have that meeting and start working again. Thank you for the nice presentation.
You encourage me to deal with polygroups, you know.
Yeah, now polygroups, it's very, as we said yesterday, it's very related to group, but it's also, it's challenging. Irena is here and Violetta is here. They know that it's challenging in a way that, for example, the number of groups of order 3 is only 1 up to isomorphism, whereas for polygroups, you will have more. 4, it's much more. 5, it's much more. So the computation for polygroups is a little bit challenging, which is good and not good at the same time. Challenging, and this challenging it make always will have open problems and always we will have work on it.
Okay, so if you are interested, so you can join to this work, because
yeah, sure, definitely. Already I have some ideas that we'll start working on, and we wanted to have that meeting. We're still waiting to finish our classes, and definitely we can do. I like this topic, and I'm interested in continuing working on it.
Okay, I hope so, inshallah.
Inshallah. Maybe next week we can meet.
Any further questions? Thank you, Altaha. Any further questions? If there are no questions online, anybody questions?
So Dr. Saba,
Dr. Saba
came back to
Yeah, and I was super excited
lost.
about your presentation, Dr. Ahmed. And of course, not next week, I won't join the meeting, maybe today, and discuss more about the open problem with you, hopefully.
Okay, you also, you have to join to us with me and Madeline as well.
Yeah, with the same projects
as before.
I'm working with now.
Yeah, as before.
Yes, dear.
Okay, thank you.
And maybe some colleagues from audience, maybe they want to join, of course. Maybe Professor Harkishan.
Yes, of course. Yeah, so it's my pleasure to have some more colleagues to join because we have many ideas, many problems, and you know it's more than one paper if we want to do on this area.
Okay. Any other questions or queries? Suggestions? If there are no questions, I must thank Professor Irfanian for wonderful talk on this hyperpartite graphs. Also, as Professor Irfanian announced in the beginning, so we are inviting you all online and offline participants for the upcoming 9th biennial Group Theory International Conference at Manipal. So all of you are welcome, and hopefully everybody should be able to attend offline here. Hopefully we are welcoming you to visit India. Probably the dates will discuss with the Professor Irfani and the team, and then we will decide the exact dates and the month. So with this, I conclude this session. Thank you very much once again, Professor Irfani and the team. Thank you, Professor Altahan and the Professor Saba, madam.
Okay.
Yeah. Thank you. Next session will start in few minutes.
Saba, I think that you can start without introduction. Already we did it.
Yes,
Just
yes.
continue.
I recognize. I'm so sorry
Continue
for
from
the
where
bad
we stopped.
connection. Just I was speaking and was having fun talking, and then the internet connection just, it's okay. So, okay, if I can continue about our new definition, is it okay?
Yes, yes.
Okay, so we got to these definitions about prime absorbing hyperideal. So in this specific definitions, we continue the same what we did exactly with classical one in ring theory and the normal ideals. So again, with our ring with two binary operations, and our ring for sure in this time is a commutative hyperring, and we already in different topics just redefine the commutative hyperring, and let B be a proper hyperideal of R. The hyperideal B is called this time a prime absorbing hyperideal if whenever, this is a definition from 2022, whenever A circle B circle C subset or NB, then for A, B, C in R, then at least one of the following conditions hold. The first one for A circle B in B, or A circle C in B, or B circle C in B itself. So, okay. So this is the definition. So the definition says that whenever the hyperproduct of three non-unit elements is contained in the hyperideal D or I, so X circle Y circle Z subset in I, then one of the following again must be happen. The hyperproduct of the first two elements is already contained in I, so X circle Y in I, or the third element belongs to the I, so Z in I. So let's have a quick example. So if we consider the multiplicative hyperring Z sub A, where A is the set of 2, 3, where the hyper multiplication is defined by X circle Y by 2xy, comma 3xy. So in this case, every principal hyperideal generated by a prime integer, for example, 5, is a one absorbing prime hyperideal. This is the same. So another example, if we just change A from the obvious or previous example to the A of 3, 4, where X circle Y, 3xy, 4xy, the hyperideal is a two absorbing primary hyperideal, but of course it's not one absorbing prime hyperideal. So there is a theorem before that. If we have R with two binary operation be a commutative hyperring and let B be a prime hyperideal of R, then B is one absorbing prime hyperideal. So this is kind of small like summary of the proof. And another result for every one absorbing prime hyperideal is two absorbing hyperideal. So there's kind of generalization of this absorbing of one or two absorbing hyperideal. Now let's come to the interesting part about this talk. So why we should introduce a prime absorbing graph. So for graphs, we provide an effective way to study algebraic structure. This is a normal way. And of course, also, many graphs have been introduced for commutative ring. And these graphs have algebraic properties, for example, connective, complete. Also, we can get the diameter, we can get the chromatic number, and so on. And in this specific definition, where the prime absorbing hyperideal play a crucial role in hyperring theory, however, no graph, of course, yet developed for a prime absorbing hyperideal. So this is very new topic. So this is why it's different from the old or extend from the classical one. So what we know about why the old classical graph, there's a limitation. So classical graph are defined using ordinary multiplication. However, in a hyperring, it's generally a set of elements rather than a single elements. And of course, also classical adjacency relations no longer captures all algebraic interactions. So we can get more results when we speak about hyperrings rather than a classical formal graph like previous graphs we already done with. So far, I think Professor Ahmed tell you a little bit about normal definitions. So I will say it again. What do we mean by connected graph, diameter, girth? I know that more of you may be familiar with these definitions. So just again, before starting with some results about our new graph and define it. So again, connected graph is a graph G is connected if every pair of vertices is joined by a path. And also, what do you know about diameter? The diameter of G denoted by dmg is the maximum distance between any two vertices of G. So the maximum distance, what just we call the diameter of G. And the girth is the length of the shortest cycle in G. And sometimes if G contains no cycle, so in this case, the girth of the graph just equal infinity. Chromatic number is the minimum number of colors required to color the vertices of G. So in this case, the adjacent vertices receives different colors. And also very important definitions for today is complete graph. So a graph is complete, like what Dr. Ahmed mentions before, if every pair of distinct vertices is adjacent. So, and we call it K sub n. Okay, what about the idea? So the definition condition of prime absorbing hyperideal involve the hyper product of three elements rather than two elements. So this is our new definition, and I'm still working with this definition. So it's just a new research. Still, I need to looking for more results, but I want just to share with you what I did so far. So in new definitions, again, are with two binary operations, the addition and multiplications. So be a commutative hyperring, and B be a proper prime absorbing hyperideal of R. The prime absorbing graph of R, we call it, for example, gamma sub B of R is the simple graph. So again, the simple graph is a graph without loops and parallel edges. And the vertices is, in this case, it's all elements of R, just excluded B, and two distinct vertices. In this case, the adjacency, condition. X and Y are adjacent if and only if there exists a vertex Z belong to the R without excluded B, such that X circle Y circle Z and B. So here we have a quick example. So Z sub A, where A again 2 and 3, we define B as the ideal of 5. Once I draw and go with the definition exactly, we have x1, x2, x3, x4, x5. We got this adjacency because X adjacent with Y if and only if there exists Z not belong to the B such that X circle Y circle Z in B. So for example, I can represent X5 with X3, X4 with X2, okay, X4 and X1, because this relation and the adjacency condition is not working. So again, some results, basics, properties. Every time once we're working, we talk about connectivity, we're talking about properties with complete, gear, diameter, and so on. So again, it's connected or it's complete if, okay, so if we suppose that for every pair of distinct elements, X and Y belong to the R and we exclude B, and X circle Y not in B, so and for every Z in R and we exclude B again, X circle Y circle Z in B, then the prime absorbing graph is complete. So far, it's hard to find a quick example, so that's why just I wrote the theorem. Okay, and also about the number of vertices. The number of vertices, if we go with finite group like Z sub M, then the vertices of this graph is just the number of, okay, the elements of Zn minus the number of the ideal elements. Okay, why we study Zn? This allows us, of course, to describe the graph by using arithmetic structures of n. So we can get many results from this, and we can then we work with different classification. My main goal next time, or hopefully within 1 week, if n having this definitions as we all the time work with, then we aim to characterize the graph of Zn in terms of the prime factorization of n. And I believe we can get some results from that. And also I'll try to working with when it's connected and when it's complete, and what is the diameter, what is the girth, and looking also to know by one of the results about click numbers and chromatic number as well. Then I'm thinking also about planarity, when the graph is planar, when it's not, and also about isomorphic thing like what Professor Ahmed mentioned about. So it will be a very long and interesting paper, inshallah. So what I also wanted to share with you some with the classical one, David and Anderson's working with zero divisor graph, and with Badawi, Dr. Anderson and Dr. Ayman al-Badawi working on two absorbing ideal of commutative ring. This paper exactly, I use it to understand how they're working with two absorbing ideal of commutative ring, but in the regular or classical way. Then I built on it what we can do in this paper. And of course, we use the, okay, this reference about Beck on 1988. Of course, also Professor Davos, Bully Groups, Theory and Related System, and different also new research working similar to this work. Okay, and also I did before 2 months this paper with the Professor Izzat and Dr. Ace, about graph associated with prime absorbing structures and still frequent. So we start working or done with this one, and I do similar thinking, but in hyper ring and hyper ideal as well. And this is what I should continue since the internet connection before, since I worked 20 minutes, then I finished right now. And hopefully everything is clear and waiting for your questions.
Thanks, Dr. Saba, for the interesting talk and connecting hyperring with the graph theoretical part. And let's check if we have any questions from our online or offline attendees.
And before this, Madeleine, I would like everyone, if he wants to work with us again, like what Professor Ahmed said, in the same ideas, we can, of course, we are open for a good collaboration in this field. Thank you.
Do we have questions online or offline? Dr. Ahmad, you're muted.
Oh, can you hear me?
Yes, Professor Ahmed, yes.
Okay, so thank you, Saba, for interesting graph associated to, again, algebraic structure and hyperoperation and hyperring, right? So,
yeah, hyperring.
as hyperring, yeah. So, as you define, you consider the definition that X is adjacent to Y if there exists an element Z such that you have the condition X or Y or Z in a subset of P, right? So we know that we may have a loop. X is adjacent to X. So that's the reason that you assume that X and Y are distinct, right?
Distinct, yes.
Because if you just put if you did not mention about the distinct, so we may have X is adjacent to X, so we may have this condition. So
if we have a loop, of course, it's not a simple graph anymore, and we should ignore this. We want a simple graph.
So that's the reason that you assume that two distinct elements, X and Y, right?
Yes.
And another thing is that Z, you mentioned that there exists an element Z. So Z is unique, or sometimes we may have more elements satisfying that condition, right?
So it's because, yes.
So you mentioned that if X is adjacent to Y, right? So we should have at least one element Z in P. So maybe we may have more than one. So it's not,
maybe one, maybe more. It depends to the example itself.
And it's not important for you. That's maybe the number of this Z related to the degree of vertex X or Y, right?
Exactly.
So
this is
important.
The idea. Yeah, very
so
important.
It means that it means that you have to consider how many Z actually exist with this condition. So that number actually for the given formula for the degree, right?
The next session will start. Yes.
Okay. Thank you very much.
Thank you for your remarks. Yes, thank you, Professor Ahmed.
Thank you so much. And now we are ready for the next session. Next speaker is ready.
Okay, thank you.
It is there, huh? So, good afternoon to all of you. Next speaker is Professor G.V.V. Himasundar. I would like to briefly introduce. So next speaker is G.V.V. Himasundar. I would like to introduce him briefly. He is the head of the Department of Mathematics at SIWS College, Mumbai. He has PhD from the Department of Mathematics, University of Mumbai. His research is on Riemann surface under the guidance of Professor S. Kumreshan and post-supervisor was Professor R.R. Simha of TIFR. He has credit of several publications in international journals, and he also authored a book that is Introduction to Calculus of Residues, published by Techno. Among many contributions in academic and research, he has credited to given the proof of Poivet's general uniformization theorem for planar Riemannian surfaces that has been published in Annals Polynici Mathematici 2011, and many other good research papers he has. He has also credit of several invited talk and presentations in international conferences. He has attended many international conferences, and specifically, I would like to recall about his participations and presentation in ICM 2010 to 2014. He also got many support of research and travel. So with his few contributions, it is to you. Today we talk on role of automorphic groups in complex functions.
Yeah, first, it's a very great pleasure to come to MIT again. I thank the organizers, especially Professor Shyam Prasad and Professor Srivas, Professor Hare Krishna. And in fact, I have interaction with all others also in the department. In fact, they visited recently, Professor Kavitan, Professor X for a conference. Thank you. So the topic is the role of automorphism groups in complex function theory. So this is a fascinating particular branch in complex function theory, where actually you can see the interplay between topology, geometry, algebra, analysis, everything in complex functions. There has been a lot of huge amount of publications by eminent mathematicians in the last 5 decades, like the branch and etc. Even in India, many people worked on this, like Kaushal Verma from IISc and others. So there are numerous applications of these groups, but I don't want to come to that application part. Well, I just want to give a glimpse of these groups in complex function and how these are related and to other branches. That's my point. Okay. So here C stands for the gap, that is C linear infinity. That is for Riemann sphere. And I take any domain in C gap to avoid any circuitry complications. Instead of taking it C, I just look at it C gap, you see, to define a connected space. So a conformal automorphism on omega. It is a 1-to-1 and onto holomorphic map from omega to omega with phi inverse. This one, phi inverse, is also automatically holomorphic. Yes, and we call it as a bihomorphic. So conformal mapping or bihomorphic mapping, whatever you can use. So under the composition of mappings, the automorphisms of omega form a group. So composition is identity works here as usual. And I'm looking at a conformal self maps of the domain omega. And our aim in this talk is to study this role of these groups in geometric function. So before going, just I give some brief study about these groups for standard domains. If you look at C cap, we know that these are all linear fractional transformations of the form Jz plus B by Cz plus B, AD minus BC is not 0. If you look at for C, there are translations like Z plus multiplied by AZ plus B, A is not equal to 0. Suppose if it is simply connected, then we have the central theorem in complex analysis, that is Riemann mapping theorem. So in that case, if it is not equal to C, we can map it onto the, it is biholomorphic to the unit disk. So the automorphism group of unit disk is infinite, so we know that. And all the, it consists of all linear fractional transformations that are e power I theta into z minus a by 1 minus a bar z, and theta is here, and modulo less than 1. These are also called Mobius transformations. This group I will come back again in the talk in future slides. The third. So if you have a doubly connected domain, it means the complement has two connected components. In that case, it has an isolated boundary point, then it will be a punctured disk. Otherwise, it can be also a punctured plane. So we denote punctured disk as D star, 0 less than, modulo less than 1. And if it is a punctured and plane, then we write it as 0 less than, modulo less than infinity. So the automorphism groups of punctured disks, they are all in rotations. And in case of C star, that is a punctured plane, it consists of all functions of the following forms. F of z is Az, A is not equal to 0. And F of z is equal to A by z, A is not equal to these two. So if omega is doubly connected domain, suppose there are no isolated points, because in this case it is doubly connected, but there are isolated point here, it is 0 in both the cases. But if there is no isolated point, then you can conformally map it into an annulus. So circular annulus, that it looks like this. So that is 1 less than, mod z less than r. I normalize this one. It means you can have r less than, mod z less than capital R. Then you can just write it as 1 less than, mod z less than capital R by small. So by normalizing, I can take it as 1 less than, mod z less than r. But only just a caution here. To apply A1 and A2, they are conformally equivalent only if capital R is equal to small. Otherwise, you cannot have a biholomorphic map between the atoms. So in this case, the automorphism group of A, in this case also it is infinite, and consists of the functions. They are of the form rotations and as well as inversions, E power I theta or by Z. So these are the total overall conformal submaps here in this case. Next, automorphism groups are finitely connected. So I have already talked about simply connected as well as doubly connected. So when it comes to finitely connected domains, I basically it is greater than 2. I also put one extra condition on omega, it is bounded and open set in C, and a smooth boundary. The boundary regularity is very important because that is a smooth means you can simply understand that the boundary has a nice Jordan curves. Okay. Otherwise, sometimes we cannot talk about boundary with some strange curves like infinite length. There are such curves, fractal type of curves or Julia curve. Such curves may be there, and in this case, it will be very difficult. So, but we are looking at a smooth boundary. And in this case, the whole whatever the domain, you can conformally map it onto a canonical region in C, such as there are different types of regions. Like if you in Riemann mapping theorem, you can map it onto this. So if it is simply connected, not equal to C. In case of doubly connected, you can map it onto angular. So similar result is there. There are different types of canonical regions, parallel slit domain, or circular slit domain, or disk minus small circular disks. So I just look at them because anytime in any proof that we would like to work it on giving a proof of such things, we have to just map the given domain onto this one of these domains. That is what we have to do. We'll just in fact, even in the case of general uniformization theorem of Kobe, if you want to look at it is a planar domain, you have to choose one of these domains and we just have to map it onto one of these domains. So this domain is finitely connected domain. So how it looks is you can annulus minus some disjoint circular arcs, and the radius of these arcs maybe on the same radius, doesn't matter. Actually, it is also taken from the annals. This is a proof I had given for Kobe general uniform addition theorem that is mapped onto this. This is actually inspiration from my doctor's book, Smiley Face. So I tried to that smiley face, she was when I was in 2009. This was she was in school fourth standard. So she used to show that for small figures. So I was inspired to make it as a connected 5, and it is also purchased from Pune. So if it is another disk, is another way you can say. So this is a connectivity 4. So you can take the disk minus, you can remove some of the disks. So in any case, you take any strange domain. It's not required to be like this. The domain can be any randomly like that. If it is a connected 4, you can somehow make it to conformally make it onto one of these domains. But these proofs are not so easy. By back and all, we will find the proofs. They are highly technical. So these are all just you can how it is not so easy. Okay, up to Alpha's book you can see maybe for circular street domain, but for this it is highly. Yeah. So the groups of finitely connected domains, the automorphism group of a finitely connected domain with connectivity greater than 2, it is a finite. So if you look at the disk, there are infinite automorphisms. But if you look at annulus, there are also infinite many automorphisms. But if you go beyond that, if you introduce one more hole or something like that, like this slave, then automatically the number of automorphisms will come down. In fact, they become finite. So, in fact, Hence gave bound for all these things. The one bound is it will not exceed n into n minus 1 into n minus 2. But in fact, in this paper given almost all studied very well, and how many automorphisms will be there. The bound, in fact, it's a more better bound. That is for 4, 6, 8, 12, 20 for connectivity. The upper bound is always 3. In fact, more stronger condition. If omega and omega dash are domains of finite connectivity greater than or equal to 3 in C, then the number of proper holomorphic maps from omega to omega dash is finite. So from this actually automorphism group is finite also will follow. This is I proved it in 2012 in Journal of Ramanujan and Society. So, but this is not the case if the connectivity is infinite. If you have connectivity greater than or equal to 3, then there will be finite number of automorphisms. But if it is again infinity connectivity, there is no guarantee. So in this case, again, there will be infinitely many automorphisms. So this is also from Ramanujan and Society. This one, this figure is taken from there. Automorphism omega need not be finite. If omega is by a holomorphic to a bounded domain. For example, I have given C minus this. You can pull out these lists, and then you can take those translations. There are infinitely many such translations. The connectivity is infinite connectivity, and even there are infinitely many number of automorphisms. So now, why the study of conformal mappings comes into picture? Suppose you have a conformal mapping from one open set to another. So we can transfer the holomorphic functions from U to the holomorphic functions. So how we can do is that you take a holomorphic function on V, then F composite H is holomorphic on U. Similarly, G U to C is holomorphic. Then G composite H and plus C is a holomorphic on V. So if you have conformal mapping from U to V, then U and V are essentially you can indistinguishable according to complex function. So we can study holomorphic functions on a rather complicated open set. So what is the use is that suppose we look at in applications, aerodynamics and etc. You have to make the wings of an aircraft. The aircraft wings are actually looks like airfoil, looks different. But that is very difficult to study, the physical quantities on that particular shape. So what is the best thing they do it? Actually, this is the real world application. They first work it on a semicircle, and then they will map, they will study on semicircle, and then they will map it onto the aircraft, the airfoil. So similarly, anything that so they can study the fluid dynamics on that, how the fluid flows. So the main thing is conformal. There are several applications. You can look at any book on Algebraic, you will find the applications of this matrix. So what is my talk is actually this one. By looking at the automorphism group, can you understand the geometry of the domain? This is the main question. If you look at the automorphism group, so whether you look at the algebraic properties of the automorphism group or topological properties of automorphism, can you understand the geometry, how that domain actually looks? So the problem is, if you look at the automorphic, two domains you have taken, and they are supposed they are biholomorphic, then you can always say their groups are isomorphic. See, the thing is like it is actually the idea of claim. How to look at the structure, the geometric structure is invariant under certain maps to study. In case of group theory, we study isomorphic groups to have the similar properties. If you look at Riemann geometry, we look at isometries. So if you look at topology, we look at homeomorphic groups. So similar maps, what works in case of complex analysis is biholomorphic maps. So it means if one domain has a particular structure, the other one also has a similar structure. So here the basic problem is the automorphism groups may be same, but in the other direction it is not true, because if the two angles, if you consider R1 less than modular less than R1, the R2 less than modular less than capital R, they are conformally equivalent. Only if capital R1 by small r1 is equal to capital R by small r. So there is no bihomomorphic mapping between these two angles. Should not touch. Okay. So we get it. Okay. 2 less than modular less than 6. So if you normalize, we can see it is 1 less than modular less than 3. And the other one is 1 less than modular less than 6. So you cannot have a conformal. Next. Not running. Yeah. No. You should change it to presentation. Sorry, I touched it.
Yeah.
So some of the first I would like to bring it your notice algebraic properties, how actually they will help us. So the first one is isotropy. So we take an element Z0, the isotropy group IZ0 of Z0 in automorphism of omega. We define it as all automorphisms which fixes Z0. So this particular that is called a fixed point of the automorphism. There are many theorems on this fixed point also. So automorphism of omega is said to be transitive. If you take any two elements P and Q, there has to be an automorphism phi such that phi of T is equal to Q. If this happens, we will say that it is a transitive automorphism. So for finitely connected domain, because the number of automorphisms are finite, when it is in that finitely connected domain. So none of them, either it is infinite as well as it is even transitive. So we can't say anything else. But in case of unit disk, we have harmonic characteristic. If you have a bounded domain and you take Z0 belongs to omega, then the isotropy group where Z0 is infinite, then omega is conformally equivalent to unit disk. So this is one you can confirm unit disk. It means the given if the automorphism group of a domain, it means you don't need whether it is conformally equal, it is a simply connector to say that. just look at it, whether it is a disk or not, you look at its planar domain, bounded planar domain, and take a point, and the automorphism group is studied. Look at its isotropic group. If it is infinite, automatically it is equivalent to the unit disk. Similarly, if you have a smooth and bounded domain with finite connectivity, if it has a transitive automorphism group, then also it is equivalent to unit disk. In fact, any one of them conditions, algebraic property, will guarantee to understand that what is the geometry of the area. Yes, the domain can be simply, you can make it conformally equivalent to unit disk. So you can put a manifold structure. Now, if you want to come into topology, so you take a bounded domain and take a point P. This is by Cartan. So phi omega to omega satisfy phi of P is equal to P, and if P dash phi dash P is 1, then phi comes out to be identity. So this you can take any two automorphisms, phi 1 and phi 2, and then you can define psi is phi 1, phi 2 inverse composition, and then that will satisfy the conditions of Cartan theorem. So you can say that this particular map, if you take any phi that is going to phi of P and phi dash P, it is 1 to 1. So the automorphism group you can identify or you can embed. You can identify with a subset of C cross C. It means you are looking at a subset of Euclidean space, some R4. So actually this is a function space, and you are trying to look at into a subset of R4. So in fact, this is again by Lie theorem that it is a Lie group, and simply saying it's a manifold. So topological group and the Lie group, there is a small difference. Topological group is just the group actions are continuous, but in case of Lie group, you require they are smooth, the group operations. Here the group operations are just continuous. In case of topological group, it doesn't insist manifold structure. Whereas in case of Lie group, you require it is generally a differential. It depends. Then if you are talking about it is a real Lie group. If you are talking about complex Lie group, then you require those operations are to be holomorphic. It's big different. So what exactly the idea here is, once you try to look at it, you are taking a group, and on group, just all of you are studying in algebra, but we are putting some topological structure. So, and in fact, we are trying to make it a manifold. So once you make it into a manifold, the given algebraic group into a manifold, you can talk about its dimension. So now let us study the dimension of this order. So these are the group actions. So the automorphism group, it is proper real analytic, and it's locally compact in the compact open commodity. That is just the uniform constants of the compact sets in case of if you are proposing under consideration, if you are putting some metric on this, then it is same as uniform convergence on compacts. So the structure of the real Lie group, and it is compatible with compact open topology, and the continuous action on a locally compact Hausdorff space is said to be proper if the mapping G cross X to X cross X, G of X going to Gx X is proper, and there is another condition. So generally they insist these things because the quotient space has to be Hausdorff. Otherwise, then you can have several Riemann surfaces are obtained in this way. So now Cartan's compactness principle. If you have a sequence of automorphisms, if it contains a convergent subsequence, the limit map is always either it will be onto boundary of D, or it is an automorphism. It means if you consider any sequence, every sequence phi j in the automorphism of D, it contains a convergent subsequence, and the limit map either maps D onto the boundary. It means it's a subset of boundary, or it has to be automorphism. One of these conditions will hold. So again, if you have a bounded domain, here the idea to say that why we want to look at it as a non-compactness is because we want to say the number of automorphisms are many. So if the automorphism group is large, then we can say the geometry of the domain is the symmetry. The symmetry is good. The degree of the symmetry depends upon the several factors. That is something like a automorphism group, number of automorphisms, or its dimension, or its transitive property, etc. So you have a domain. It's non-compact if and only there exists a point P in omega and Q on the boundary of omega such that limit of phi kp is equal to Q, where phi k is a sequence of automorphisms on omega. In fact, I have just given an example here. I want to look at transcript. So for till what time I have to? My time and set.
This is 5 minutes.
5 minutes more. Okay. So this, you take out the 1 minus 1 by k. This is inside the disk. So 0 to 1 minus 1 by k. Call this automorphism as phi k. So because that is transitivity. So for any 1 minus 1 by k number, there is there will be an automorphism. For 1 minus 1 by k, 0 if you take, there is an automorphism phi k. So such automorphism sequence you construct. Then what will happen is limit t tends to infinity, phi k of 0 is equal to 1. So you can say that you can apply this particular Cartan's theorem and you can say that it is non-compact. So understanding geometry again, in complex function theory, saying a group large means it contains many biholomorphic mappings. So the domains of non-orthogonal groups, they exhibit high degree of symmetry, and transitivity is one such property that it keeps the shape of the domain in fact unchanged. Okay, these are the dimensions of automorphism groups. So you can say which of them you can to understand the geometry. If you look at the bounded domain in CR, the dimension that is number crosses n square plus 2r. In case of angulars, the dimension is 1 because we have it is actually the group is isomorphically S1 cross C2. The one of them was C2 means cyclic group of two elements. So inversions, being a discrete with a leaf structure, it will have a dimension, it does not contribute. So only what will have is the S1. So the dimension is 1. In case of automorphism of D, it is 3 because unit is z minus a by 1 minus a bar and multi with e power I theta. Theta is 1. And even if you know A, that's a complex number. Again, 2 variables. So total dimension 3. In case of automorphism of C, it is dimension 4. Az plus B, A is complex and B is complex. So you can have again 4 real parameters. So in case of greater than 2, it is discrete. So by observing them also, you can say one of them, the structure of the group, the geometry of the domain you can understand. So now the working problems are many in this. Many of them are studied here in Riemann surface theory, but in the plane domain infinite connectivity, they don't know anything much about that, whether countable and countable. And which groups in these things can be extended to several complex variables here, and as well as high dimensional complex manifolds. What I have just brought you is just in planar domains. You can go to Riemann surface theory if you are interested. I think due to next 3 minutes, I just would like to skip this Riemann surface ideas here and just these are the conclusion. Just wait even after conclusion, I have little bit. No, so because I had to add it. We have a conformal bijection between two domains that already I explained this. So you can say that it is resolved by conformal equivalence constraint. Points are mapped by F, curves are also mapped by F, angles are preserved, invariant metrics are transported, symmetric groups are identified. Thus, the conformal map transfers the entire geometric structure from U to V. Okay, this is actually my talk, but I was looking in last few days how this automorphism, because basically I work in this. I don't have much anything about the fuzzy sets and all. I never studied. In fact, frankly speaking, I had to see the definition of it in the last few days. And then I thought that whether I can connect something with automorphism to this, but see that whether it will be helpful. But I can't answer any questions on the next 3 slides. I apologize because it's new. So this is fuzzy set on the unit disk. I tried. So you can membership function. There will be V of z 1 minus mod z. I defined it. So the corresponding fuzzy set will be looks like this. So the interpretation is here points near the origin have high membership, right? Okay. And points near the boundary will have low membership. So, well, if I have mu of 0 is 1, mu of 1 by 2 is 0.5, mu of 3 by 4 is 0.5. Okay. So, an automorphism, an automorphism is called fuzzy automorphism. To define it as mu of phi of z is mu of z. So, since mu of z is 1 minus bar z, we can take mod z. We obtain mod of phi z is equal to mod z. Therefore, this sort of things is preserves Euclidean distance from the origin, and basically this, you know, the Schwarz lemma from that we prove that these are all nothing but rotations. So what we can use this one? So if you are having a wireless router which is located at the center of a circular grid, so routers you put it here, then actually this automorphism defines this. Mu of z is 1 because the points near to the router will have a higher this thing, and at the boundary they will have, in fact, won't contribute anything. We won't get the that one. So I don't know how it can be applied on. So that's all. These are some.
Thank you so much. Thank you so much, Professor.
Thank you.
The question is only the topological automorphisms. So, homeomorphism between domains.
You can see.
What I say is,
Yeah.
for the compressed train, you have it on that. Take this topology, not the compressed train. It's so.
The complex. I think
The topology will be not what I say is, what to be the type of automorphisms. If you avoid the automorphic pattern,
the basic problem here is that if you are quantification of various states, this only has to be map on suppose boundary, then we require whether we can extend it or we can do such problems are very then it is a Jordan type.
the point is, in the automorphic case, you have a different domains, you get the same group.
But that won't fit us because
You get the same.
because the basic problem is if you are having a suppose we look at a torus, okay, torus looks at torus, you can just look at like this anyway, you can pull it at all. It won't give you same structure, but because homeomorphism you are talking, so it's like it's not to the torus. But if you are talking about analytical structures, they will be different. You know, Reynolds perspectives are different. So homeomorphism actually won't help for us in everything. Only analytic
Ultimately, there's a.
yeah. But this is not. Yeah, that's because the analytical structure depend on 3D minus 3 parameters.
Okay, so thank you so much, Professor, for your nice talk.
Yes, yes. We have prepared session 440. 440.
440, 30.
Actually, 436.
430. Okay. Oh. Because otherwise, my time will.
Yeah.
But you look at it very sort of it's
Comes with digits.
That's very good.
Was that?
He is back. Good afternoon, sir. Bhaskar, sir. Hello. He was there. He was checking the slide system. Bhaskar, sir.
Whether he has muted or something.
Maybe that's good. I will check.
Whether he is.
He was checking the slides just now. Maybe he just went out for a minute or so before the talk. Because just now we finished checking the slides. After sharing. We told the 4:40 point. That's what I think. He might have want to get ready.
Just for the song.
Anyway, I asked him to unmute.
That's why I didn't take this.
Second starts.
No, he's not there.
Or I.
రెడీ రెడీ ఉన్నా
Yeah. Good
Yes.
afternoon, sir. Bhaskar, sir.
Sir, good afternoon, sir.
Can you hear me?
Yes, sir. Your voice is good.
Yeah, sir. This is Jagadish from Mahe, Manipal.
Sir.
Yeah. I will introduce you to the audience
Sir.
first, sir. Afterwards, we can start your presentation.
Sure, sir.
Yeah. Good afternoon to all. I am introducing Dr. L. Bhaskar. He is Assistant Professor in the Department of Mathematics, National Institute of Technology, Raipur. He earned his PhD from Kakatiya University, where his research focused on contribution of near rings and vague near algebras, and has been serving NIT Raipur from 2022. Dr. Bhaskar's research interests include fractals, fuzzy set theory, and near algebra. He published highly important papers in several high-quality journals. With his recent contributions in fractal geometry, vague near algebras, and neutroscopic algebra, he actively guiding PhD scholars and has delivered invited and keynote lectures at national and international conferences, and continues to make significant contribution to the contemporary algebra and its applications. Today, we had a talk by Sunil Jacob John on fuzzy set theory. Sir's talk is also related to fuzzy set theory. Title of his talk is Modern Tens in Fractal Geometry Using Fuzzy Set Theory. This is the introduction of Dr. L. Bhaskar. Sir, now you can start your talk, sir.
Yes, good evening to all. My voice is audible, sir?
Yes, sir. Your voice is audible.
Yeah. So, good evening to all. First of all, I would like to express my sincere gratitude to the Dr. Kuncham Shyam Prasad sir and the management of MIT Manipal for inviting me to deliver an invited talk at the 60th International Conference on Algebraic Hyperstructure and their applications. So, shall I start, sir? Hello?
You can start, sir.
Yeah. So, uh, uh, so my talk on the modern trends in fractal geometry using fuzzy set theory. So we know that is the nowadays the peoples encounter fractals everywhere. They are found their livings and inanimate nature, and also used in science and technology and art. So generally, the geometry, that means classical geometry, fails to describe the complex nature forms like mountains, clouds, trees, and lightings. So you can see it in this video. I think you can see it in this video. That is all are the fractal which are available in the nature. So that in Mandelbrot given the idea of fractals, and he's given the geometric framework to the irregular and fragmented shapes. So Mandelbrot given a very famous words about the fractals. That is, why is geometry often called cold and dry? One reason is its inability to describe the shape of the clouds, mountains, trees, shears. So clouds are not spheres, mountains are not cones, and coastlines are not circle, and the crust is not smooth, and lighting does not travel in a straight line. So nature shows us not a just higher degree, but a completely different level of complexity. The number of different length scale in the structure is always infinite. So this is the famous words about the fractal given by the Mandelbrot. So that what is the fractal actually? So that the term fractal was introduced by Mandelbrot in 1975. So derived from the Latin word fractos, meaning is broken and fragmented. So the fractals are geometric structure that exhibits complexity and fine structure at every scale. So generally the fractals are generated by simple iterative and recursive process, but display high complexity boundaries. And the fractals generally are geometric structure that exhibits mainly we have. So any figure after that is we can see the figure in the nature. So to identify this figure is fractal figure or not. So based on these three properties, the first one is self similarity. Any figure has the self similarity. That means that the pattern repeats at every scale. So that is the second one. Generally, it is a non-integer dimension. The most of the fractal the dimension of the fractals are non-integer dimensions, sum of the integer. So that means that the fractal dimension exceeds the topological dimension, and it has infinite detail. That means no matter how far you zoom, new structure will appear. That means what generally. So you can take one fractal structure, right, and cut it small part, right, and zoom it. Then you got the whole that is figure. So that is the infinite detail. So fractal offer a mathematical framework for representing complex and irregular shapes that cannot be easily described using the classical geometry, showing hidden patterns and structure within appears chaotic form. So this is the definition of fractal. So generally, based on their iteration process, that we can classify different type of fractals, right? So the first one is the iterative function system. So that is the first type. That means, so the iterative function system constructed through repeatedly affine and constructive transformations, so applied to an initial shape. So these transformations generate exact self-similarity, making the result structure purely deterministic. That means what the best example is Sierpinski triangle and Barson sphere. That means Sierpinski triangle means what generally. So we can take the equilateral triangle. That equilateral triangle has the three equal sides. That means and each equal side the fix the middle point and connect all the 3 minutes point. Then after connecting the three middle points, then you got the that is four the triangles, and the middle part is have to delete, right? Same procedure we have to, after deleting middle part, then you got the three angles, that is what, three angles, then those three angles are equivalent to triangles, then again three angles, that is got the had the three equal that is the equal sides. That means you can again you have to fix the middle part, then you connect them, then you have to repeat the same procedure, then you got the, that is Sierpinski triangle. This is the best example for the iterative function system. The second one is escape time fractals. So that is what, so escape time fractals, this is second type of the fractal generally. So this is escape time fractal is also generated by the iterating a nonlinear complex function and classifying the point based on the whether their orbits remains bounded or diverge. So they exhibit iterative boundaries and extreme initiative to initial condition. The best example for this is Mandelbrot set and Julia set, right? So we are this talk is based on the, so we mainly focus on the escape time fractals only, right? So this is the best example of the Mandelbrot set and Julia set. So one more, that is a type, that is random stochastic fractals. So random or stochastic fractals are created by using the probabilistic rules and random variation. These fractals capture the statistical self-similarity observed in the natural phenomena like coastline, mountains, and clouds. The best example from this one, so Brownian path and diffusion limited aggregation. So likewise, the another type of fractals are there, that is the L system and space filling fractals, right? So based on the recursive grammar, substantial rules often used to model biological structure or space filling curve. So the example for this, it is fractal trees, Dragon curve, and Hilbert curves. So some other type of fractals also there. So whatever we discussed in the previous day, those are the very mainly three types of fractals, four types of fractals. Now the other type of fractals are some Stranger attractors. So these arises from chaotic dynamic system described by nonlinear differential equation. So the orbits of such system settle into fractal shape trajectory known as attractor in the space. They illustrate sensitive dependence on initial conditions, a hallmark of quick theory. So example for this, Lagrange attractor and results attractor. So inverse are derived fractals generated by the reversing or modifying iterative rules of classifying a classical escape time function. These fractals often revolves complementary structure to their parent sets, introducing new visual symmetries and patterns. So the example for this, Nova fractal and an inverse Julia set, right? So physical imperial fractal also one type of fractal. So now we are focusing on only escape time fractals. So what is the escape time fractals? Escape time fractals are generated by the simple iterative mathematical function and measuring how quickly the sequence diverges to infinity. That means what? How quickly the point that is crossed to the escape radius generally. So the very famous example is the Mandelbrot set and Julia set. The first one is the Mandelbrot set and the second one is Julia sets. Both are the core idea. Yeah, the escape time fractals, the core idea comes from the complex number Z0 with the iterative function Zn plus 1 is equal fc of Zn. And here we measuring how iterative it takes for mod Zn to exceed the predefined threshold, that means escape radius. So point that never escape. So from the interior, while those escape after different, iterating often the boundary of the exterior. That means the point, the points never escape the formy interior of the Mandelbrot set, right? So what is the Mandelbrot set? What is the definition of Mandelbrot set? The Mandelbrot set, it is denoted by M, is a set of complex number C for which the quadratic function f of z is equal z squared plus c. So that is does not diverge when the iterative form z is equal 0. So we can write this is a mathematical representation. M is equal, that is the C belongs to complex number, that is fc of n belongs is bounded. So where fc of n means what is n is a number of iterations. So mathematically, the Mandelbrot set is a compact and simply connected subset of complex plane. Its boundary exhibits infinite complexity and display self-similarity, where the version of the entire set, often called baby Mandelbrot and set. So generally, we can, that is what the escape time visualization and properties of Mandelbrot set. We can see it in this video. So we can, you can zoom it, you can zoom it any small part of the Mandelbrot set. Again, you got the Mandelbrot set. So this is the visualization. We can see the video, then you got the more information, right? So that is Mandelbrot set is a visualized using the escape time algorithm, where each complex parameter C is iterated under the quadratic map FC of Z is equal to Z square plus C. So points whose orbits remains bounded are colored in the block, and while these that escape behind the threshold are assigned color based on the how quickly they are diverge. This visualization rewards the intricate and recursive nature of this set, right? So you can see the boundary exhibits infinity complexity and it displays the self-similarity. You can see in this video the boundary. So that is a very high complexity. So what is the Julius set? So in the generally in a Mandelbrot set, so that is the C is a fix. So say that Z is a fix. Z is equal to 0 is a fix. But here in the Julius set, generally we can the complex number C is a fix. That is a difference between we can see the same, that is a formula is same. FC of Z is equal to Z square plus say C. But in the Mandelbrot set, is it Z0 is equal to 0 is a fix. But here C is a fix. But here in the Julius set is one of the fundamental objects in the complex dynamic are named after the French mathematician Gaston Julia. It mainly represents the boundary between the stable and unstable behavior of the iterative map in the complex plane, right? So for a fixed parameter C, the quadratic map defined like that, FC of Z is equal to square plus C. And what is a filled Julia set? Filled Julia set means what? So that the interior part, whatever the interior part is there in the Mandelbrot set, that is the filled Julia set. And what is the boundary is there? The filled Julia, that is a Mandelbrot set boundary, it is called that is Julia set. So it is denoted by JC is equal boundary of KC, right? So KC defined like that. Here KC is equal, C is equal some value. So that is C is equal this value, the figure is like that. So if C value changes, maybe figure will be changes. That is not different C value, we got different Julia set, right? The different C value we got here, so different figure. So that is a speciality of the Julia set. So now, so that is how we link with escape time fractal, and that is a uncertainty. So that is what that is right, that uncertainty here fuzzy. So that is fractal boundary such as Mandelbrot set and Julia sets exhibit infinitely complexity at every scale of magnification. So classical set theory cannot capture the classical set theory cannot capture that level of uncertainty. So which motivating use the generalized framework that handle the partial membership and boundary of vagueness. So that we know that the fuzzy set definition, generally fuzzy set is defined by the Jada in 1965, and he allows the partial membership where each element has a degree of belonging ranging between 0 and 1. So this is the definition of fuzzy set. A fuzzy set A over the inverse set Cx is defined by the membership function mu A. It defined X is a non-empty set x2 closing with 0, 1. And here it is that assigned to each element small x belongs to capital X. A degree membership, we define A is equal x comma mu of x, and x belongs to capital X. That means it is a, so that is a mu of x is a membership, that is a membership, that is a degree of membership of element X. And what is the intrinstic fuzzy set? The concept of intrinstic fuzzy set introduced by Autonomous in 1986 extend the classical set theory by simulating considering the degree of membership and degree of non-membership. Here we are adding the degree of non-membership to the fuzzy set. So that we got the here intrinstic fuzzy set. We can define here that is a intrinsic fuzzy set A, the universal A is defined like that. A is equal the X element and degree of membership and degree of non-membership, and the sum of degree of membership, non-membership always between 0 and 1. And also we define here that is a hesitation degree, that is a phi of x, that is equal 1 minus degree of membership and degree of non-membership of x. So what is the intrinsic fuzzy Mandelbrot set? So that is we have connected with the intrinsic fuzzy with the Mandelbrot set. So basically, intrinsic fuzzy Mandelbrot set is a defined intrinsic fuzzy set. It is denoted by M bar, that is what C, mu C, and mu of C. So where both that is a membership or non-membership satisfying the, so the we can define membership like that and non-membership that. That mu of C is membership function, and here mu of C is equal 1 when. So that is the FC, that is nth iteration. That is what nth iteration at the point is always less than or equal to. Here that is less than 2 means what? Here it is generally less than 2 is the escape radius. So if the point does not exceed the escape radius, that time the membership value it is 1. If the point escape, that means what? Here in the second one here we can see the FC of k minus 1 by FC of k mod. So that means here it is what at kth iteration, the point exceed the escape radius. That means exceed the, it's crossed the boundary. So that, and k minus 1, that is the kth iteration, the previous one iteration, that is k minus 1 iteration, that is k minus 1 iteration that does not exceed the escape radius. So in this case, we can define like that. That is what mu of C is equal mod FC k minus 1 of 0 by FC of k of 0. That means 0 is a Z naught. Z naught generally we take here 0. And non-membership function it is 0 when if the point does not exceed the escape radius, that is 2. So that time it is 0. If the point is exceed the escape radius, that means here you can see the second one. That is FC of k is greater than 2. That means what at kth iteration the point is exceed. And k minus 1 means this previous one iteration. That means k minus 1 iteration does not exceed. So that time we have to define the function like that, non-membership function. So that is lambda k, and lambda k is equal to be defined here. That is scaling function generally we call here 1 by k gamma. Gamma belongs to 0, 1. This is now if you have defined here, there is hesitation, there is uncertainty also. That is what in the intrinsic fuzzy Mandelbrot process, hesitation phi c represents the degree of uncertainty that arises when the point exhibits both inclusion and exclusion tendency. That means phi c is equal, we can define. So 1 minus mu of c and mu of c. So that is equal, we define like that. It is 0. So that is if the point does not exceed the escape radius, then value is 0. If kth iteration the point is exceed, and the k minus 1 iteration the point does not exceed the escape radius, that time we have to define this one 1 minus 1 by k gamma 1 minus something this one. And here FC of n of 0 is equal mod FC of n minus 1 of 0 square plus c with initial condition z is equal 0. So here we can say observe. So 1 minus 1 by k gamma increases with k, and the hesitation phi c grows with the number of iteration required for the escape, indicating greater uncertainty near the Mandelbrot boundaries. This behavior captured the institute that the point closer to boundary of Mandelbrot set exhibit the ambiguous belonging, so lying in the transition zone between the membership and non-membership. So for example, if you take here, that is for a Mandelbrot intrinsic fuzzy Mandelbrot set. So for you can take C is equal 1, C is equal I. So we can generally we take Z naught is equal 0, that is initial condition, that C is equal minus I. So that means what the first iteration, that means generally that is mod Zn is equal that is mod Zn is equal Z minus 1 square plus C generally, right? So Z naught is equal 0. The first iteration the value is minus I, the second iteration minus value is what? Minus 1 minus I, and third iteration we got I, and fourth iteration minus 1 minus I. So you can find the all the iteration mod value. If that mod value does not exceed the escape radius, that is 2. The mod value less than 2. So that time we have to that is C is equal minus Y. The membership value mu of minus I, that is C is equal minus I value 1, because by the definition we can see you can go for here. So that is if nth iteration the escape radius does not escape the escape radius. So that time it is it value is 1. So that for C is equal minus I, the c is equal to minus I, the point does not escape the escape radius. So that mu of minus I is equal to 1, since so this nth iteration less than or equal to for all n belongs to n. And non-membership value, we can see for non-membership value that is that v of minus I is equal to 0. Here also we can, that is the escape radius is always for nth iteration, any number of iteration, the value is does not escape the escape radius, so that the value is 0 and degree of uncertainty. So these values is based on the that formula, that is what intrinsically Fuzzy-Mandelbrot said, and for c is equal to minus I value. So and phi of minus I is equal to 0 and mod that is modulus of that is that particular number of iteration, that is less than or equal to. And belongingness is what generally c comma mu of c and nu of c. So that is a c comma mu of c, mu of minus I value is what generally it is 1, c value minus I, and mu of minus I value 1, and mu of minus I value it is 0. So that is belongs to the Mandelbrot set. This is the first example. You can take the second one. So per se, I take c value different, minus 1 plus I, and initial condition z0 is equal to 0, right? So that at z0, at z1 is equal to 0, and for the first iteration, the value is minus 1 plus I, the second iteration minus 1 plus I, and third iteration minus 1 plus 3I. That means what generally you can, at third iteration, you find the mod value, that is a mod, z3. So that value is what always is always it is escape. That means it is always greater than 2. So that the escape that is escape value is what n is equal to 3. That means third iteration is what escaping. So that now that condition, the membership function, so mu of c value is minus 1 plus I is equal to what generally you can apply here this formula. This formula, the second one is this formula. Then you got the here, that is a you got the here, that is what here third iteration, that means the second iteration by third iteration. So the second iteration value is what minus 1 plus I, and third iteration value is minus 1 plus 3I. Then we got root 2 by root 10, then approximately 0.44. So that is, and also non-membership factor nu of c is equal to minus 1 plus 3I. So that you can use the here the non-membership value, that is here this is mu c. So lambda k into something, this one. Then we got here that is what nu of minus 1 plus I, that is 1 by that is a k power gamma. Here k is equal to 3 because the third iteration the point is escaping. So that, and you can gamma value between 0 comma, you can choose any one, 0.3 or 0. Whatever you want. So minus into 1 minus, so the function value, that is what that is a third iteration, second iteration by the third iteration, that is modulus of the second iteration by modulus of third iteration. So we got the, after simplifying, we got the 0.39, and degree of uncertainty it is also, it is you have to apply the same formula here. Degree of uncertainty, it is 1 minus 1 by k gamma, 1 minus something, this one. So then we got here that is a phi of c is equal to what minus 1 plus I, that is this value we got 0.155 like that. And what is the belongingness in intrinsic Fuzzy-Mandelbrot said, that is what c comma mu of c nu of c, right? C value is what minus 1 plus 3I, and what is the new value 0.44 723, and new value is what 0.3975577. So this is a belonging to the Mandelbrot set M. For different c value, we can computing different, you can take whatever you like, you can choose c value, and you have to apply that formula, right? So here c value I take 0.8 plus 0.3I, right? So that the first iteration, generally z0 is equal to 0, that z1 is equal to what z0 plus c, that means z0 value is 0, so that the that is z1 is equal generally c, so z is 0 point, and z2 is equal, that is first, second, and third up to 9th iteration. So after 9th iteration, here you can find the mod's 9th iteration. So that time the point is escaping to escape radius, that is escape radius 2 here, right? Escape radius. So that, so the escape value n is equal to 2, and now what is the membership function? You can apply the same story, mu of c. What is the c value here? And this value, after calculating, you applying that formula, the intrinsic Fuzzy-Mandelbrot formula, then we got here 0.590497, and A non-membership function also we can calculate here. That is a nu of C value. C value we know already. So that we, after calculating, we got here 0.211829, and degree of uncertainty is also, that is what, phi of C, that is we got 0.197 something. And what is the belongingness here? That is a C comma mu of C, nu of C, that is the belongingness. So what is C? You know, what is 0.8 and something. And we got here membership value, this one, non-membership value, this one. So that is also belonging to the capital M, right?
Hello.
So
Bhaskar,
now,
sir.
Sir.
Hello. Sir,
Hello?
5 minutes. Within
Okay,
5
sir.
minutes, please conclude.
I will finish, right? Sir,
5
here,
minutes.
here generally, here we find the different, that is a membership functions, non-membership function, degree of uncertainty. So the all the membership points value is formed in this type of figure, that is a visualization figure. Degree of membership formed like that. Degree of non-membership, this one, and degree of that is uncertainty formed this figure, right? So you can collect all those things. These are the main results, theorems, sub-theorems. I can skip this one. And here also I can skip theorem, some proof. So, and here also I can skip here, right? Now, finally, that is a Mendel bulb fractal. Generally, so Mendel bulb fractal is a 2D structure of the Mendel-Broad set. So here we are using different spherical coordinates and the Cartesian coordinates. And if we have to, we are using here some iterative function. So that based on that, we can define the Mendel bulb fractal. And here one more, that is a dynamic Mandelbrot fractal. So dynamic Mandelbrot fractal, to achieve the dynamic Mandelbrot fractal, we have to use different type of operations, that is the time dependent translation, time driven rotations. So these are then finally we are dynamic iteration. We can use this one. We can see the video. So we can see the here also dynamic Mandelbrot fractal we can define like that. And here also we are using a distance estimator. So for calculating the distance between 2 points. And this is a very beautiful figure actually, video actually. We can there is no time. So we can see this is here we publish a very good journal, that is a Kevo solid and fractal, very top journal. Recently we published this paper. And yeah, these are the few references. Thank you, sir. Once again, I thank you, the organizer, for inviting me for a deliberating lecture, 60 International Conference on Algebraic Hyperstructure and their applications. Thank you, sir.
Thank you, sir. Thank you, Bhaskar. Any questions from audience, offline or online? Yeah, otherwise we thank Bhaskar sir for informative talk on fractals and connecting it to fuzzy set theory. Thank you, sir.
Sir.
Thank you, sir.
Okay, sir. Right.
Thank
sir.
you.
Can I leave, sir? Right. Okay.
Let us thank Dr. Jagadish B for chairing the session. Our next speaker is Professor Om Prakash from IIT Patna. The title of the talk is A Realism of Cyclic Force over the Matrix. Now I request Professor Avanish Kumar Chaturvedi from University of Allahabad to chair the session. Please.
Next speaker is and he is a professor at the Department of Mathematics, IIT India. He completed a medicine in mathematics from Patna University in 1999 and PhD in mathematics from University. He has 23 years of teaching and research experience in institutions Like graph theory and like number theory. So here many areas will be working now. She has the credit of publishing more than 108 research papers in different referred international journals of reviewed and 16 papers in the reputed conference proceedings. Here organized 16 training programs as a coordinator, organizing secretary, and member of the organizing committee of more than 25 conferences for staff training programs. Today, we will start. It is titled as a revisit of cyclic mode over the matrix field. So I want to add one thing. Actually, as I just read out, with research interest in rings, modules, and algebraic potential, algebraic graph theory, and algebraic number theory. So due to his motivation, I also started from rings and modules to algebraic coding. So his motivation for many of us. So thank you, welcome, sir. And so
thank you so much for introducing me. And first, I would like to thank the organizer of this conference for inviting me, giving me the opportunity to discuss my work. Of course, that's the recent work, and hopefully participants audience can enjoy with the author. So as you are looking the title, the visit of cyclic course over the matrix. So a little bit I would like to elaborate the topic. Even though in algebraic coding theory we have been working over the linear codes. But in fact, the class of linear codes is very vast. Many classes inside the linear codes are there. One of is the cyclic code. So initially, coding theorists work over the codes, work over the field. Later on, it has been moved towards the finite ring. From finite field to finite ring. And now these days, of course, these all are commutative structures. But now these days, because matrices are very helpful to us for the practical application. Even many whatever software have been coming, they have been using entries in terms of the matrices, column matrices. And from the MIMO, whatever the electrical circuits have come for the transmission of information, one of these MIMO. That has been also utilizing the entries or identity as the matrices. So working over the matrixing, initially it was a little bit challenging. The reason behind that is matrixing are non-commutative. Even though you are defining over a commutative ring, but matrixing is a non-commutative. So going ahead for the construction of code, restricting, initially you will have to consider the finite field or finite ring over which you are going to consider the matrix ring. And later on you will have to again restrict them so that it would be a finite ring. So these are really a bit tricky. And later on you will have to decompose them. So whatever code you are going to obtain, you will have to decompose them. And during decomposition and finding the representation as the direct sum of service spaces, submotives, that is also a little bit challenging. But anyway, we have initiated 4-5 years back, and finally years back, the first came over the matrix through. And this is one of. So initially we work for the linear codes, not restricted whether we are going to find out cyclic codes or consta cyclic or skew cyclic. So initially we worked over the linear codes, and then we impose the restrictions so that we can do only for cyclic. So even though in the linear code cycling coming, but specifically I'm going to discuss here for science. Even though other things are also there. So this is the plan of presentation. I a little bit said about it. So initially I will recall the basic of algebra as well as coding theory. And then we will move towards the structure. One of is RP, that is M3 over FP plus UFP plus U square. In fact, MP over F2, F3, FP has been already done by some other researchers. So we took the generalized structure. That's the chain name, but if considering the matrix over it, that will become the dimension. And after M3, we move for the higher order matrices. So that is we considered M4. So initially we have worked for that is considered the matrix setting of matrices of order 4 over F2, and then generalization came F2 plus U, F2 plus U square F2. Still we will have to generalize for the FP plus U, FP plus U. So initially we did for these two structures, and then whatever the conclusion that I will. So what is this? It's not one small. It has been going bad. Yes. So as you all are aware about the rings, non-empty set with two binary operations satisfying certain axioms. Satisfying certain axioms. So now you can see that's known as ring. Well-known examples we should have. And every ring has certain ideals. So and ideals are very helpful to us. Context of vector space, which is over the field. Whatever every vector space is, every field is a vector space over itself. And whatever ideal we should have, we can also consider them as the subspaces later on. Or if underlying field is appropriate to the ideal, then we can look for the subspaces. Sometimes in case of vector spaces, we can fail if field is bigger than the ideal. But in case of modules, that is most comfortable. Every ideal is a module over the. Right? And we have concept of left ideal, right ideal. So whenever we are considering the non-commutative structure, so often we are going to operate the commutative structure. Case of non-commutativity, we are often going to consider or find the modular structure in spite of vector space. So ideal, then polynomial ring. That is one of the, you can say, highly impactful terminology in mathematics that has been bridging the algebra as well as for information technology. Whatever the information we should have, of course, we have been fixing the positions. And we are ultimately able to associate each sentence or even you can say each word by a polynomial. We are able to present. So ultimately collection of polynomials we should have over certain fixed alphabet, set of alphabets. And ultimately we are looking for the algebraic structure. And if it is a ring, then of course that is helpful to us. Whatever algebraic things are available to us, we are utilizing them and moving on it. So this is one of the important notion. And now you can see coefficients coming from a ring. Then we are calling these all polynomials over that. And ultimately under addition of polynomials, multiplication of polynomials, that's again. So after polynomial, just I have included about the field. And of course, vector space concept we have. Then you can look the module, whatever conditions for a vector space we have. Just we are replacing field by array and going to get the module. Of course, everything is not has unity. So whenever we have unity, then last we are looking for last one condition of vector space. 1 into x equal to x. If it is so, then module is said to be unitary. So similarly, we have concept of submodule like subspaces in the vector space. So non-empty set of the module, which is also a module under the operation of the module, which is known as sum. And these are few well-known examples. Any arrangement you can use a module over Z. Similarly, each ring is a module over itself. And of course, n module of R, a module over. In case of vector space, we have guaranteed that every vector space has a list, except 0. When in case of 0, some of it is written as an empty set. But for any non-zero vector space, we have a basis. But it is not true for the module. And from the practical application point of view, we would be more comfortable if generating set is known to us. That is, basis is known to us, but we have concepted vector space. But since in case of module, it is not true that every module has a basis. So we are compromising with one of the conditions, because for the basis, two things are needed. A non-empty set of a vector space which is linearly independent and generating each element of the vector. So we should have to compromise with one of the conditions, to which we can compromise and to which one we can go ahead. Of course, independency would not affect for making the representation of the elements, but generating set is most important to know the situations of all. So we are compromising with the independence. So that's why we have concept of finitely generated. The model has a subset, finite subset, which has been generating each element of that model. Then we are calling model is finitely generated. If that finite subset is also linearly independent, then it becomes its basis. A module has a basis means that module is known as field. That module is known as field. So these are the things. Now I would like to come to the basic definition of code. Of course, that's the representation. We have sequence of alphabets, collection of alphabets, systematically arranged. That would be meaningful whenever we are talking about the information that's statement, sentences, and that has certain meanings. Okay, so code is in fact the collection of sequences of alphabet symbols. And in a code, we have many sequences. So each one sequence of a code is known as its code. That is, each element of a code is known as its code word. Since we are aware in any sentence, whatever words are there, it's not compulsory or necessary that all words have same number of alphabets. That is, whatever different words used in a sentence, number of alphabets differ. Okay. So there is no any issue, but for the mathematical calculation, computational point of view, we haven't also classified what happens. Is it possible that whatever words are there, all are of same number of alphabets are? So again, polynomials have been helping to us in this way. Because whatever, suppose for one word, you will have a an associated polynomial of degree 3. For another word, we have polynomial of degree 5. Next one have polynomial of degree 2. But the facility provided by mathematics is that even though you will have a polynomial of degree 2, we are able to write it or consider as the polynomial degree 5. Just you will have to give the coefficients of higher degrees 0. So you will have a polynomial of degree 2, you will write 0 into x3, 0 into x4, 0 into x5. And finally, the number of coefficients for self-interest that can be made equal amount of. So whenever a code in which each code word has same number of alphabets, that code is called block. So block code is ideal from computational points of view, and we can do it very hard without loss of symptom. So a block code means length of each element of code C is fixed. If C is a block code of length n over FQ, this means C is the subset of n of F because in alphabets are there that we can obtain just by taking Cartesian product of FQ n times. So by that way, we have been going ahead. That's an example. And about linear code, as I said you, it has linear structure. That is, these are subspaces or submodules over the set of alphabets that's either a field or finite field of finite. So the main reason why the reason of this work, why we have been going to work over the matrix towards that I would like to, and of course especially the linear. So that's the flow chart. Of course you are aware. We should have information. We should have information, and then encoding is going. Whatever the machine language we are converting them, that has been propagating in form of the waves, and then reaching to the receiver end, and their decoding process has been doing, and after decoding, in fact, receiver getting the actual information. Of course, during transmission, certain changes would take place in the information. So the main aspect of a unique coding theory technique is that as much as possible, we secure our actual. So that is the main thing. And towards that, we have been trying to obtain the codes with better parameters. So of course, this is the literature review. Related that is codes obtained over the matrix, and now you can see here, main work has started for the codes over matrix from 2013 onwards. Right. So initially it was considered over the M2 F2 first one. Then in 14 it is over M2 FP. And then in 19 one of paper came for M4 F2. Then in 2019 to 22 itself, in fact work has been completed in 21 itself, but published in 22 by my group over the M4 F2 plus UF2. And then in 24 again we worked over M3 FP, that is generalization took place. And now we have worked for M3 FP plus UFP plus U square FP and M4 FP plus UFP plus U. So last one work is here. That has been worked. So question is coming why we are extending this structure. So see main emphasis in coding theory to get the better code. Whatever code we are obtaining, that is our greater code. Or that should be MDS. That is whatever the codes have been obtained previously. Code rates, either code rates should be better or parameters should be beating the previously obtained. So that it has good impact in the communication. And secondly, where we can implement these codes. So as I said you in the about the channel, that has been directly utilizing the codes obtained over the matrix or in form of the matrices. So that's why we work over this, even though it has been not appreciated. And inclusive journals have already communicated the paper. So comments is coming, same comments is coming. Even though you can obtain these codes over the general structure, while you are working for the matrix and giving such a bigger computation. While over matrixing computational complexity is increasing. So these questions have been coming, but it has certain reasons. So, of course, one of my work is already accepted in quantum information processing class. So that is also over the matrix. We have obtained also. So we have considered these two structures, as I said you earlier, RP and first we will discuss about this structure, construction of codes, and then in the second part we will see over the M4, F2 plus U, F2 plus U square. And as I said, we are looking for the addition. So now you can see first we have established that this RP, this range is isomorphic to this one under these conditions. So that general representation can be visualized and we can do computation. And after showing its association with the other algebraic structure, that is the isomorphic structure, we move towards the decomposition. Of course, for the construction of code, we are considering the quotient ring. So Rx modulo xn minus 1. And since we have already well established result for the cyclic codes, that whatever the irreducible decomposition of this idea, xn minus 1 in fact, each one is responsible for the cycle. The classes of codes may not be called cyclic, it is well established. So we have considered cell cyclic codes. And then with the decomposition, of course, we have defined the map, reduction map. Then later on, we will see the plate.
The previous slide, U cube is equals to 0.
Now you can
Previous.
yes.
From U is element of itself. U belongs to where?
See, U is the element of FP itself.
Just P.
FP itself.
U cube is equals to 0.
No,
U
see.
is equals to 0.
In fact, we are treating here U as the variable because we are going to consider the polynomial. Am I right? Polynomial indeterminate U. And later on we have been evaluating. But if you will take U3 is not equal to 0, then what happens? The structure will go ahead there. Am I right? It will not stop at the square. So that's why we have imposed this condition. And secondly, whenever we are considering the quotient with the ideal generated by such type of elements, U3 minus 1 or U3 plus 1. So, you know, in case of quotient ring, whatever the ideal with respect to quotient we are obtaining, that is ultimately the zero element of the ring. So, after that degree onwards, terms have been terminated. So, ultimately, we are going to get that. Someone has been considering U3 equal to 1. Right? So, under different conditions, we are looking for the yes, so that we can control the system, control the structure. Yes.
That's where this nothing coming, that RP kind of.
Yes.
Because of that.
is there any advantage for stopping for UQ? Like, can generalize this? FP plus PFP plus U.
Yeah, you can go up to UN minus 1 and you will impose condition on UN. UN is 0 or UN is 1. So whenever UN is 1, then you will take UN plus 1. Then what happens? That is ultimately U because UN is 1. So UN into U, ultimately U. So club with the previous. That term is clubbed with the second one.
27 we need, I think, RP. So at what how many steps we are getting that RP, I think that is important. That will give the final advantage.
Correct. So with this, and of course, as you are looking at delta map, that has been associating again the structure RP is the matrix thing. And now we are going to do FP3X because ultimately we are obtaining the codes over a field. Parameters should be from a field. That's a finite field. So that is the association with these two structures. Of course, basically we have been starting working over the matrix ring. Ultimately have to move towards the field so that we can obtain the parameters. So under this map we have been there. And then from FP3X, that's the again polynomial ring, we will move towards the field FP. So ultimately parameters should be from there. So that you can see. These are few results. As I said, you decomposition we have been doing. So now you can see xn minus 1. We are assuming these are the factorization irreducible factor of xn minus 1. So we have already well established result. Each of our is possible to generating a set. Right. So by that way, we have been going ahead and established few results. So if n be such that p is not dividing n and this is the representation of xn minus 1, then Rpn is the direct sum of Rpx modulo f. That is corresponding to each polynomial irreducible polynomial. What algebraic structure is coming? Original structure is assumed. Direct sum. Similarly, some other results have been established. Of course, in case of being non-commutative ring, so it's very hard to know about initially the situation of the ideals and the submodules. So initially we have computed the ideals manually. So these are the manual computational result. So first we computed the ideals of this ring manually, and that result we have discussed for this. And then we again move towards the further results. Similarly, RP module, RP X modulo, ideal generated by xn minus 1 again has irreducible pairwise prime polynomials in this, and these are. So ultimately, that's the sum. So with these results, of course, we move towards the decomposition now. What codes we have been considering and what are the submodules we have seen in terms of the represented code. So that component wise we can do the calculation and finally taking their sum we will obtain for the codes. And we have also calculated the cardinality degree of the polynomial so that later on we can move towards the construction of dual codes of the obtained. Because for the quantum codes, towards the application of quantum codes, duality must be checked. When codes are self-dual, then we are going to look for the codes. So that's why we have also calculated the. So after this all, of course, gray map is defined as I said you, so that we can move towards the field. And then quickly I would like to go ahead because time is completed. So I would like to show you the obtained code. Suppose these are the results with certain restrictions. And now you can see all the parameters of the code, length of the code, rank of the port K and Hamming distance of the port D. So with this all, now you can see some examples, some professional examples, and we have list of examples. So these ports we have obtained over the matrix ring M3 over FP plus Q, FP plus Q. Same thing we did for the matrix ring of order 4, that is M4 over F2 plus Q, F2 plus Q square F2. So, like previous, we have established the basic results, look about the decomposition, then computed the ideals, then we move towards the sub-modules of the respective rings. Of course, computational work increased a little bit, being matrices of order 4. But after this all, establishing the result, just I would like to show this. Now examples has come, and these are codes we have obtained over the second one structure. Still few works are left. The codes we have obtained, but being matrixing, 8 we have not systematically studied about the decoding process of each codes. So that part, of course, a little bit we have already done, but systematically we have not presented this for system. So that part we will have to look at. And secondly, whatever different structure we consider good, later on we will have to look for the construction of quantum or how it can be implemented towards the data storage in terms of the DNA code or other codes. So that we will have to see. So these are the few things. Of course, conclusions I already said it. These are few references. Thank you so much for listening. That's the last lecture for I think 5 minutes. No problem. Are there any questions from audience? Yes.
So when we exist already M3 of FP or course or M3 of FP or M3 of FP plus Q and construct. So what is the advantage of constructing M3 of FP plus FP plus U square FP compared to these two?
Yes, as I said you, and also shown the list, we have chances to get the better code than the previous. Then you can see my paper, one of paper is already accepted to early on. So we have obtained the better code, QFDS codes. And secondly, whenever we are generalizing the structure, of course, that's not the necessary often you will get going to get that. But in this case, we have already obtained. So that's why we mentioned. Sometimes we are generalizing just to look the complexity, increase the complexity so that you have a separate work different from the previous. But here our purpose is to get the better. And that.
Is there any chances to get still?
For example, whatever code you will obtain over the Z4 or ZP in Z4 or Z. Many papers now these you can see now these days. You can see the papers over the mixed structure like ZP square something. That is 2-3 structures have been taken together. So what happens? It has been observed that the chances of better code is increasing. So that's why they have to run. Of course, that is not so appreciable because concept is already established for ZP, and same way you are going to do for the mixed structure. But if you are going to get the better code, then of course that can be accepted by the code. Because ultimately purpose is to get the better code so that will help during the competition. Right? communication.
Are there any other question?
Here, the cyclic code definition is like as it is non-commutative thing.
No. Definition of cyclic code is same.
Any left or right idea?
A code C is said to be cyclic if it has a code word C0 plus C1, C0, C1, C2, C3, Cn, which is in C implies Cn, C0, C1, C2, that will be in this.
Like in terms of quotient.
Either from the left or right side would be there. That would be in C, then we are calling code side. Definition is same. But that is a little bit easier, algebraically little bit advanced. So that's why we have consequence.
Like if left ideal is there, then left shift is.
See, depends upon the situation. Very sometimes we can calculate from the right side, but once you will have to fix. Anyone you can consider what initially you are fixing for your definition of cyclic code accordingly. Go ahead throughout. Yes.
Yes, sir, one last.
Yeah, please.
And so for this matrix, over the matrix, have you got some MDS codes like
Yeah, few MDS codes are there.
Yeah.
Not many.
Yeah.
But few MDS.
Yes, that is sufficient. We are getting some.
Computation is large, and of course that has been taking time. Sometimes magma has been also not giving the distance.
Okay, sir, thank you very much for
Yes, it's
very much. Okay, sir, thank you.
Let us again thank the speaker and Avanish sir for chairing the session. Here is an announcement. Tomorrow, the contributed sessions will commence from 11:10. Thank you.
Sir.
Bye bye.
Where are you? What's that? Yeah. I need to keep the jacket. What? The code is this. I will.